Hello and good evening. So I'll be going over a new Dorado release and talk about some of the work we've been doing in Dorado over the last few months to make it faster, more accurate, and easier to use. Then I'll share a bit more about what we plan to work on next. So today, we're releasing a new version of Dorado, version 050, and this is a big release for us. The beginning of the year, our goal was to bridge the gap between Guppy and Dorado in terms of the core features. And I'm happy to say that we've made tremendous amount of progress on that front. Dorado now supports sequencing summary files, barcode demultiplexing with custom barcodes, DNA adapter and primer trimming, which was just released today, DNA read splitting, and alignment with Minimap 2, along with a lot of other features. We've also integrated Dorado into Minnow and made Dorado the default base color across all of our devices. And all of this has been happening in parallel with continuous improvements to base calling speed and accuracy. So I'm happy to share that today, with this release, Dorado now implements all core features from Guppy. So if you're still using Guppy for any of your offline base calling use cases, please switch over to Dorado. If you run into any issues, feel free to reach out to us, and we'd be happy to help you through them. But we haven't just been implementing or re-implementing features from Guppy. We've actually extended Dorado to have more functionality as well. So for example, today, as part of V050, we're releasing automatic model selection. Now, instead of having to specify a full model path, you can just specify a shorthand notation for the model variant you're interested in. And based on the data set that you've provided, Dorado will automatically figure out the best version and run condition to use. We've also released a hemimethylation support, which is a new feature for Dorado Duplex. With that, you can now mod base call both strands of a DNA molecule simultaneously. My colleague Marcus will be talking more about this in his upcoming talk. We're also releasing a new simplex model, and I'll be talking more about that in the next couple of slides. Then a couple of weeks ago, we actually did another release of Dorado that was focused more on RNA updates. As part of that, we added RNA methylation calling, specifically for M6A in the DRATCH context. We added RNA read splitting and adapter trimming, as well as an initial implementation of poly-A tail estimation for both cDNA and dRNA. My colleague Aino will be discussing more of these in her talk. So the latest version is now available on GitHub. Please head over to github.com/nanoprotect/Dorado, and you can download the pre-built binaries and get going right away. So now I'll talk a little bit more about some of the model highlights from this release. So as part of V050, we're releasing a new simplex base calling model that we're calling version 4.3. In terms of headline metrics compared to the previous version, which is V4.2, the hack model remains largely unchanged. There's a marginal improvement in error rate, but the sub model sees a 15% reduction in error rate, putting the median accuracy for sub around Q23. But the headline metrics don't actually tell the full story. The new base calling models perform much better in low complexity regions, specifically in regions with a lot of CT-rich repeats. So to measure the improvements, we looked at the change in the number of dropout regions by aligning reads to the human reference, specifically the T2T-V1 reference. So reads that were called with the new model, V4.3, saw a 70% reduction in the number of dropout regions compared to the same reads when they were called with the previous version of the model. That actually brings down the total number of dropped bases across the entire human genome to less than 50,000 bases. This is actually really encouraging, and we expect that this improvement would help anybody working with nanopore-based assemblies. Of course, we're not just going to stop there. Our goal is to bring down the number of dropped bases to 0. But we also saw something quite fascinating when doing this analysis. The number of dropout regions actually improved not just with the base calling model, but also with the reference use. So going from T2TV0.6 to T2TV1, we again saw a reduction in the number of dropout regions. This tells us that the underlying read quality is actually better than it seems. And in fact, the read quality is actually running ahead of the quality of the reference itself. Now, similar to the low complexity regions, we also see improvements in the telomeric regions. So in the IGV plot here, on the top half, we see some reads that were called with hack V42 model, aligned to a chromosome 6 telomere region. And on the bottom are the same reads that have been called with the latest release model. We can see qualitatively that the newer reads align in a much cleaner fashion than the older ones. There are, however, still a few consistent errors that we see across both of these models. but we suspect that these errors are not actually read errors, but reference errors. We plan to work with the T2T consortium to investigate these more, and if they do turn out to be reference errors, hopefully we can integrate those back into the reference in the next version. So last month, we released a research model on Vario that was focused on improved bacterial isolate calling. Since then, we've incorporated all of those updates into our production model training pipeline. And the new version that we released today includes all of those updates in the fast, hack, and subvariants of the model. So the graph on the right shows the median consensus accuracy improvements across those models. So between the research model and v42 sub, we already saw quite a bit of improvement last month. But when we retrained those models with the latest production pipeline, we actually improved over the research model as well. So some strains improved more than the others, but in general, the median consensus accuracy went from about Q45 in v42 to more than Q50 in v43. Now, for context, bacterial strains are pretty small. They're only a few megabases long. So Q50 plus consensus accuracy means less than 100 errors across the whole genome once fully assembled. So these should be really exciting results for anybody working with bacterial strains. So obviously, we made fundamental improvements to the base calling accuracy, and I imagine many of you will probably want to rebase call your data. But rebase calling can be time-consuming, which is why we actually spend a lot of time improving the performance of the model as well. So I'm happy to share that Dorado V050 runs 20% faster than the previous release. So on an A100 compute tower, the Dorado hack model can hit 355 million samples processed per second, which is roughly 28.5 million bases called per second. Now, for reference, a P48 sequencer can generate 150 gigabases of data over 72 hours, which is about 27.7 million bases generated across all 48 flow cells. Now, you can probably guess where I'm going with this. So with the V43 model and the latest Dorado build, we now have hack base calling keep up with the P48 sequencer over 72 hours across all 48 flow cells. So this is a really critical milestone for us to hit in terms of performance. Right now, this is only available in standalone Dorado, but we are working hard to get this into Minnow and release it as soon as possible. Now, there were a few key things that helped us get to this performance number. So one, we doubled down on intake quantization. So now all of our LSTM layers and linear layers do their math in integer space as opposed to floating point space, and that gets us the higher throughput that we need. Two, we re-implemented a lot of our convolution and linear kernels using the NVIDIA Cutlass library, and that actually gave us much better utilization of our GPUs. And three, we started moving towards managing our own GPU memory instead of the libtorch allocator, and this helped us resolve a lot of memory fragmentation issues, as well as improve the batch sizes that we can scale up to. So in the interest of time, I'm not going to go into too much detail, but if you're interested, please feel free to check out my colleague George Calling's talk from London Calling earlier this year. All right, so what's next for Dorado? So we're going to continue exploring new model architectures to push the boundaries in terms of base calling accuracy and get that in your hands as soon as possible. Performance, of course, remains a key focus for us. So we want to use more of the accelerators on the Apple silicon, as well as extend GPU support to the next generation of NVIDIA hardware. iPad base calling is something we're actively working on, and we're making quite a lot of progress on that front. You'll actually be hearing more about that in a talk tomorrow. Then FOSS5 deprecation. So Dorado has been Pod 5 first from day one, and in an upcoming Minnow release, Minnow will actually be outputting all raw data in Pod 5 by default as well. And over the last year, the Pod 5 tooling has also improved significantly, so it's now easier and faster than ever to convert your old FOSS5 datasets to Pod 5. So we've decided that with all of those improvements, we're going to drop support for FOSS5 from Dorado in the next few months. Finally, focus on stability. So we've been adding a lot of features, but we want to shift focus a little bit to improve reliability and stability so that our users get a much more seamless experience using Dorado going forward. So all in all, our goal still remains to make base calling faster, more accurate, and a much better user experience for all of you. And that's it for today. Thank you very much.